Good morning, students. Coming to you live from my own house today. We are going to start with Chapter 7. It is our last section before we would have reviewed for the AP exam. So today we're going to start with 7.1. It's the area of a region between two curves. So beforehand, we had already talked about area of a region under a curve, the area between the curve and the x-axis. We want to expand that and talk about the area of a region between two curves. So let's look at an example and try to think about exactly how we can adapt what we already know to put it together and attack a seemingly more complicated question. So first things first, we need to figure out what region we are working through. So let's make a quick sketch. We've got y equals x squared plus 2. Hopefully you guys can graph that rather quickly as the quadratic up 2 units. And we've got a linear function y equals negative x. So for example, 0, 0, negative 1, negative 1, positive 1. When x is 1, y would be negative 1. So I've got this nice, easy linear function going in this direction. They've also given us some boundaries. X is 0 and x equals 1. So that would be x is 0, the y-axis, and x equals 1, another vertical line. You want to think about these 4 curves that they've given us as your fence lines or your boundaries when you're trying to decide which region you are finding the area for. So this shape right here is what they are referring to. Now, if you want, take a second and hit pause and think if you can figure out a way to take what we've already learned about area and come up with a way to calculate the area of the entire yellow region. Hit pause and just make a guess, see what you can come up with. And I'll pretend that you've already done that, and I'll spill the beans here. So what we've already talked about is in earlier chapters, in chapter 4, we've talked about the area underneath the curve. And when we say underneath, we always imply underneath the curve and above the x-axis. So for example, this area that I'm sketching in here in green, we could calculate that area by finding the integral from 0 to 1 underneath that quadratic function, so of x squared plus 2 times dx. We could also compute the area underneath, right? We could go ahead and set up, and it's in blue here. Blue maybe wasn't the best choice, but next to that green. But we can calculate the area underneath by doing exactly the same thing, by calculating the area between 0 and 1 underneath the curve, so minus x, and above essentially the curve, but below the x-axis. The thing is, this part will calculate out a positive value because that area lies above the x-axis. And this portion here would generate a negative value because, as we've discussed, when your area is below the x-axis, you compute a negative area. We don't want to consider that area negative. So rather than adding that negative area, we can subtract it. And that would allow us to come up with the area between the two curves. You can think of it another way, that you are creating those Riemann sums, that you're building those rectangles, and you are adding this portion of each of those rectangles, but subtracting this portion down here of each of those rectangles. That's another way to sort of think about how to generate the area formula. And we've spent time talking then about how you can split up, but here let's put it back together and say that this is the integral from 0 to 1. I have the same bounds on both of my integrals, and I can just condense those two into 1. So I would have x squared. If we want to keep them in order, we would have plus x and plus 2 times dx. And I could go ahead, this is my area equals equation, and I could finish it up, right? We would have x cubed over 3 plus x squared over 2 plus 2x evaluated between 0 and 1. That would give me 1/3 plus 1/2 plus 2 minus 0 when I plug in all of the zeros. What's that going to come up with? We'd want to move over to 6. So this would be 2 6 and 3 6. That's 5 6 plus 12. That gives me a total of 17 6. So there you have it, a method for coming up with the area of a region between two curves. Just a side note, you should be able to do them by hand. For example, this is a relatively simple equation here, and such a problem could appear on either the calculator or no calculator portion of your AP exam. When you're doing your homework, and I'll do the rest of the notes here the same way, if you like, because I'm going to assume that you already know how to integrate by hand, especially on something nice and simple, go ahead and just use your graphing calculator. For those of you stuck home without one, in the letter that I sent, there are some links at the bottom to online graphing calculators, apps for your phones that you could download and work through so that you're not stuck cranking out everything by hand. As a refresher, press math, go up to number 9, function integrate, and it should pull up a nice heading just like what we set up on paper, and you can type it in. We've got x squared plus x plus 2, and this last little bit, you just want to make sure your variables match, and it'll do the hard work for you. Notice here I've got a decimal. Quick cool trick, hit math, and it'll convert your decimal to a fraction when possible, and so I can see that my answer was correct. The box in the center here is our attempt at generalizing this idea and coming up with sort of a formula. It's not a very complicated formula. Kids usually like working with the area formulas because they're pretty easy to do. So the formula for area, leave yourself space. I'm going to write 2 of them, is to integrate from A to B. So these are your bounds. Where did you start? Where did you stop in the x-axis with your area? And of f of x minus g of x times dx, affectionately referred to as top curve minus the bottom. And this is for any time when you're constructing your rectangles in a vertical manner. So we've got that here where our bounds are x values, x equals a to x equals b. There's another version of this formula that says that you can construct your rectangles and move side to side. So rather than constructing and creating your Riemann sum going vertically, you can construct your Riemann sums horizontally. We'll do our last example in the notes with that method. So we're going to have area equals the integral, again from A to B, but this time over here, remember these are x values. When I set it up in this manner, these would be y values. And we'll still have our first function, but this time with respect to y, minus our second function with respect to x, or sorry, with respect to y again, and then dy at the end. In that case, in order to find the height of your rectangle, you would actually be taking the rightmost curve and subtracting the leftmost curve. So you can think of this as the right curve minus the left. And again, we'll do an example at the end. Most commonly, A and B are not given, so oftentimes you will have to find them by looking for intersection points. So solving systems back in Algebra 2 or pre-calc will be helpful here. Let's try an example together again. So first up, create your sketch. We want to find the area of the region bounded by these 2 graphs. We have a parabola. The negative makes it flipped upside down. It's still up 2 units. So we'll just make a quick sketch here, up 2 units. It would go through at like square root of 2, so about 1.7. So it looks something like this. This would be my f of x. And g of x is just the linear function y equals x. So we can imagine this sketching that in. Let me extend my parabola just a little bit. We want to think about the area of the region bounded by. So we need these two curves to create a fence line for our region. And the region that it is implied here that we are calculating for would be this one right here. It would be important for me to find the intersection points here and here to figure out what those A and B values should be in my formula. So if you recall, right, 2 minus x squared is equal to x. We've got to solve a quadratic, x squared plus x minus 2. Quick factorization here. Let's see, we would need a plus 2 and a minus 1. That would multiply to negative 2, add to 1. So that would make my coordinate here at negative 2. And since y equals x, let's plug into that one. And at positive 1. So that gives me a nice detailed graph. Remember, if you're using your graphing calculator, you can also find your intersection points using your calculator. Just depends which tools you have handy while you're working. So for example, I can type in, let's see, what was it? 2 minus x squared and y equals x. Let's make sure we're zoomed in. And as a quick refresher, they will let you use it on a calculator question. We want to calculate number 5, the intersection points. You do have to do each one individually. Move your cursor close to where you think it intersects, press enter, enter, and then one more time enter, and it should give you your values. And again, we could find the other intersection points simply by moving our cursor over, press enter 3 times, and I can verify my solutions. Again, I don't mind if in class you are using your graphing calculator to come up with those values or to create even the graph. But remember, on the AP exam, you may be expected to do that by hand. It just depends upon where you encounter the question. Sometimes students will ask me how I knew that it didn't go down here. That would be an unbounded region, right? It would still be, if I gave this area down here, it would be bounded by the parabola and the line, but it would keep going down forever. I would not be able to calculate the area of that region. So I wanted it to be a closed region in order to have a set answer. And now I can think of it as I'm constructing my Riemann sums by creating those rectangles. It would work perfectly fine to do vertical rectangles and work with the dx formula. Another hint for that is that everything's written in terms of x's. So what I'm thinking to myself when I set this up is that I'm calculating my area. The x values where I would think of creating rectangles are going to start at negative 2, stop at positive 1. And the top curve, the curve that's controlling the top of each rectangle, is the parabola. So I'll have 2 minus x squared. And then I would subtract the bottom curve. Here, that bottom of my rectangle is always determined by the linear function. So I'm subtracting x. And then I want to include my dx. You're welcome to try it by hand. I'll show it to you quickly on the calculator just to keep our work a little bit shorter here. So let's see. I can't do it in the screen, actually. It does not set itself up for me to do it on here. You are probably best served by going into the math heading on the main page, choosing again option number 9, and then calculating what you set up. So from negative 2 to 1, 2 minus x squared minus x, and we've got our dx at the end. So I typed it in just like that. Press enter, and I got 4.5. It's an exact value. Doesn't really matter if you use decimals or fractions, whichever you prefer. I think I'll stop here to keep the video size a little bit more manageable. We'll flip the page, check out the link for the second half. We're going to do a couple of more interesting things with this.